Hello students, welcome to the channel Top Gate. In this video, I will introduce you to the concept of theory of automata and formal languages. But before going on to the concept of theory of automata and formal languages, I will first introduce you to the concept of theory of computation. Okay, since we are dealing with the branch of computer science, how do the computers process anything? How do the computers compute anything? So what are the steps they take in order to compute something, in order to process something? All those steps I'll be discussing here. Okay, so what is theory of computation? Theory of computation has three pillars, okay, namely language, the first pillar, automata, the second pillar, grammar, the third pillar. Okay, so one by one I'll explain to you all these three pillars. So first of all, come to the language, the first pillar. The building blocks of a language are, the first building block is symbol. Okay, so what is a symbol? So language, we are talking about any language, like say we have English language, we have a Hindi language, we have a Telugu language, and so on. Okay, so n number of languages are there. Okay, the first thing in a language is a symbol. So what kind of symbols we are using in a language, that will be called as a symbol. Like we can use A also, we can use B also, we can use C also, we can use 0, 1, 2, and so on. So anything which is defined by a user, that is an abstract or a user defined entity. So a user can define any entity. Okay, so A, B, C, 0, 1, 2, star, hash, anything can be taken as a symbol for a language. So that is the first building block of the language. Okay, now the second building block is, we are starting with the say the ground floor, that is the ground floor, and then the first floor, and then the second floor, and finally on the top floor I'll be getting my language. So these are the building blocks of a language. Now the second building block of the language is the alphabets. Okay, now alphabet is a finite set of symbols. Okay, so it should be a finite, it cannot be a infinite. Okay, so what does that mean? Whenever I am trying to make a string or say a word, suppose I am talking about English. In English there is a word called as say boy. Okay, so this boy is made up of three alphabets, B, O, and Y. Okay, so if we talk about the symbols, so in symbols for an English language we can have A, B, C, D, E, F, G up to Z. All the entities, all the user defined entities can be there. Now out of that I have taken three symbols, B, O, and Y. Okay, so this B, O, and Y will be the alphabets for a word called as a boy. Okay, and this is denoted by sigma, that is sigma is equal to AB. So whatever symbols we have taken from the symbols list for an alphabet, that will be called as the sigma. So in this case the sigma will be BOY. Okay, so the symbols can be anything, and from those symbols we take something, and that will be called as a alphabet, that is the finite set of symbols. Okay, and it cannot be empty also, that is sigma cannot be empty, that is we should have something in sigma. Okay, we should have something in sigma, and it should be a finite only. I cannot take infinite alphabets in a sigma. Okay, that is your second building block. Now the third building block of the language is the strings. So what is strings? It is a sequence of alphabets. Okay, now why we are taking a sequence of alphabets? To make a particular word, to make a particular string, we have to select some alphabets. Okay, and these alphabets came from the symbols. So first thing is a symbol. From the symbols we take something out, that becomes your alphabet, and with that alphabet I try to make a string. Okay, so that string can be called as a sequence of alphabets. Okay, like suppose we have sigma is equal to AB. Okay, so from sigma, if I have to, from this sigma, if I have to make a string, then I can make several strings, like I can make A, I can make B, I can make AB, I can make BA, I can make BB, and so on. So all these are strings, A, AB, BA, AA, 0, 1, 1, 1, anything. So whatever is there in sigma, with that sigma I try to make a string, that will be called as a string. Now finally the language, that is the top floor of the language. Fine, so what is the language? Language is a collection of all possible strings. Fine, so Suppose we are talking about English language. So in English language, there can be n number of words. So all those words, all that collection of all possible strings will be called as a language. So all these words, whatever words are possible in English language, I collect them together, that will form as a particular language. Okay. Now let's see, if sigma is equal to AB, okay, so I am talking about AB only, that is from the symbols I have taken only two characters A and B. With that A and B, now that becomes my sigma, and now with that AB I'll try to make several strings, and with that strings I'll be making a particular language. So L1, what is L1? L1 is a language. So the L1 is equal to, suppose I say sigma to the power 0. Now sigma to the power 0 means it is set of all strings of length 0. Okay, that is from the alphabets AB, I am trying to make some strings, I am trying to make some words of the length 0. So whenever we are talking about length 0, that will be called as epsilon. That is an empty string. There are no alphabets in that one, and only the alphabet is epsilon. Okay, so for sigma 0, we have epsilon. Second language, L2. Suppose I say L2 is equal to sigma to the power 1. What does that mean? Sigma to the power 1 means set of all the possible strings of length 1. Okay, so we can have in this one, because we have sigma is equal to AB, so we can have a string called as A, a string called as B. Okay, if I say L3 is equal to sigma to the power 2. What does that mean? Set of all strings of length 2. Okay, so out of AB, how many words can I make? How many strings can I make? I can make AA also, I can make AB also, I can make BA also, I can make BB also. So all these are the possible strings in this case, sigma to the power 2. Okay, clear? So we have these examples. So if we come from the top, that is the first thing that we have is a symbol. Okay, with this symbol, I take out some characters and I call them as my alphabets. Okay, that is represented by sigma. Now with this alphabets, I try to make a strings, that is a sequence of alphabets. So I use this AB and I make strings. Okay, and I use these strings, that is a collection of all possible strings under some conditions, and that will be called as a particular language. So this L1 is, in this case, the set of all strings of length 0. So this is a language. Okay, that is length of set of all strings of length 1. In this case, that is again a language. So in this language, only 2 words are possible. In this third language, only 1, 2, 3, 4 words are possible. In this language L1, only epsilon is possible. Okay, now suppose I give you some word. Okay, suppose I give you a word called as boy. Okay, and I ask you with which language this word belongs to. Okay, so what you will do, you have your Oxford dictionary, you open that dictionary, and in that dictionary, if you find that word boy written in there, then you will tell me that this boy is a English word. Okay, similarly, suppose I give you a word as AA. Okay, and I ask you with which language this AA belongs to. So what you will do, you will just simply see that AA is coming here, so you will tell me this AA belongs to L3. Okay, suppose I give you a word A and I ask you with which language this word belongs to. So what you will tell me, you'll just check all these languages L1, L2 and N3. In L2 you will find A, so you will tell me this A belongs to the language L2. Now how you are able to answer my question? You are only able to answer my question because what you are doing, in L3, suppose you have 4 words, 1, 2, 3, 4. So only 4 possible words are there in this particular language. So what you did, you have stored all these words into a finite memory. So you have some finite memory, and in that finite memory you have stored all these words. Okay, now when I ask you a question that with which language this AA belongs to, so what you did, you took this word and you went to the finite memory where you have stored all these words, and you have started comparing this word with the words stored in the memory. So one by one you were comparing, and finally you found a match and you said that this word belongs to L3. Fine. So you are just comparing, and if you are finding a match, then you are answering my question. Okay. So In L3, you have 1, 2, 3, 4, only 4 possible words. In L2, you have only 1, 2 possible words. In L1, you have only epsilon, that is one possible word only. Okay, so in any language, if the number of words is known, is finite, that is called as a finite language. So all these can be called as a finite language. Okay, all these are called as a finite language. Now suppose I give you one more language, that is L4, and L4 is, suppose I ask you to make all possible words that starts with A. Okay, all possible words that starts with A over the sigma is equal to A comma B. So the alphabets I have is A, B, and in the language what I need all the possible words that are starting with A only. So in this one, what words I have? I have A, that starts with A. Okay, I have AA, this also starts with A. I have AAA, that also starts with A. I have AB, that also starts with A. I have ABB, that also starts with A. I have ABA, and so on. So in this one, practically I have infinite number of words possible. So this kind of language is called as a infinite language. Okay, so infinite language. Now if the language is infinite, that is the number of words in this language are unknown, I am not able to store this infinite number of words in a finite memory. Since the memory that we have is a finite memory, so we are not able to store all the words of this infinite language into a finite memory. Fine. So suppose I ask you and I give you A, B, A, and so on. Okay, and I ask you with which language this word belongs to. So you might not be able to tell me, because you have to take this word and you have to compare these words with all the words stored in the memory. Now for this, suppose this word belongs to this language, but for this language I am not able to store all the possible words into the memory. So if the words are not stored in the memory, we are not able to compare it. Okay, so since we are not able to compare it, so we might not be able to answer this question. Okay, so the storing of the words into the memory is only possible for a finite language and not for a infinite language. Okay, but we'll be getting many infinite languages. We have to do all this because we have to find out this word, with which language this word belongs to. We have to do that. So how we'll do this? So for an infinite language we use automata. For an infinite language we use automata. That is the second pillar of theory of computation. So for a finite language it is very easy. We just have to store all the possible words into the finite memory, and we have to just compare the word with all the possible words stored in the memory. If there is a match, then that word is a part of that language. But if the language is infinite, where it is not possible for me to store all the possible words into the memory, then it is not possible for me to compare this word with the words stored in the memory. Fine. So for this, what we do? We use a automata. Okay. So now I'll tell you what is automata, and then I'll tell you what is a grammar. So what is automata? Automata is a system where the energy, the information is transformed and transmitted to perform certain function without the direct participation of man. So what is automata? Automata is a system where the energy, the materials, the information are transformed from one form to another to perform some computation without the direct participation of man. That is called as a automata. Okay. Now in this automata we have certain characteristics. The first characteristic is the inputs. So we'll apply some input at any particular instant of time. Okay, that is represented by I1, I2 and IP up to IP. Okay, and then this input is transformed into certain things, and then finally we get some output. Okay, that is output 1, output 2, output n up to output q. So at any instant of time the different output is produced from this machine, that is the automata. Now while performing the processing of this input, this automaton transits from one state to another. That is, while converting the input to the output, it transits from one state to another. That is Q1, Q2 up to Q1. Okay, so these are the characteristics. That is, the input is there, the output is there, and a state is there. Now this automaton can be of different types. Fine. So one is finite automaton with output, and one is finite automata without output. Okay, so we'll study both of these here. The first one is finite automata with output. In this one we'll discuss MEALY, Mealy machine. The second one we have is Moore machine. Okay, and in this one, that is the finite automata without output, we have DFA and we have NFA. Okay, so we'll study both these automata, FA, that is DFA and the NFA, Mealy and the Moore. Okay, so this is your automaton. Now the last thing is the grammar. Now let's discuss the last pillar of theory of computation, that is the grammar. Okay, so first of all, let's try to understand what is the connection between a language and a grammar. Okay, so we have started the journey from the language and then we went to automata, and now we are on to grammar. So first of all, we should know that what is the connection between the language and the grammar. Okay, so this language and the grammar, they are interconnected with each other. Language is incomplete without a grammar, and a grammar is incomplete without a language. Okay, suppose I give you certain words. I give you suppose U, ARER, and then HOW. So I give you three words and I ask you with which language these words belong to. So what you will do, you will go to the finite memory. That is, finite memory in this case is a dictionary. Okay, so you will go to the dictionary, and in that dictionary you will compare all those words stored in that memory with the words that I have given to you. That is, you will compare U with the words stored there in the memory. You will compare this R with the words stored in the dictionary. You will compare how with the words stored in the dictionary. If you find a match, you will tell me that these words belongs to the English language. Correct? Now, if I try to make a sentence out of these words, suppose I write You are how. Okay. Now, does this make any sense? No, this does not make any sense. Why? Because we haven't used the rules of the grammar in this. Okay, if I use the rules of grammar in this one, then only this can be made understandable. Okay, so I can speak English. That is because I know the rules of grammar. You are understanding English because you know the rules of the grammar. Okay, so if I apply the rules of grammar in this one, I'll write it as how are you. Now I have applied those rules in this language. Now this sentence becomes a understandable one. You can understand this particular language now. Okay, so grammar is very important for a language. Okay, so language contains a particular words, and to make these words understandable, I have to apply the rules of grammar into the language. So this is the brief connection between the language and a grammar. Okay, now grammar is of four types. The first one is a type 3 grammar. Okay, so we have type 3, type 2, type 1, type 0. So I'll explain to you one by one, and in the upcoming videos we'll be discussing all these grammars and with which machine they can be implemented. So the first one, the type 3 grammar, is called as a regular grammar. Now this type 3 regular grammar is implemented by a finite automata that we have already discussed, that is NFA and the DFA, Mealy and the Moore. Okay, so this regular grammar is the type 3 one, and there are maximum number of restrictions in this grammar. Okay, so for this grammar we'll be using a finite automata, that is NFA and the DFA, Moore and the Mealy. Okay, then comes the type 2 grammar. Type 2 grammar is called as a context free grammar. It is implemented by pushdown automata or a PDA. We'll discuss this also in the next videos. And then we have a type 1 grammar. So type 1 grammar is a context sensitive grammar, and it is implemented by linear bounded automata, or called as the LBA. Okay, and the final one, that is the type 0, is a unrestricted grammar, and it is implemented by a Turing machine. So there are no restrictions in type 0 grammar, and there are maximum number of restrictions in a regular grammar. Okay, so it is like a hierarchy. Okay, so whatever can be implemented by type 3, that is the finite automata, can be implemented by type 2. This can be implemented by type 1, and that can be implemented by type 0. So practically type 0 can implement all these things that can be implemented by finite automata, by pushdown automata, by linear bounded automata. Okay, and type 1 can implement the language of type 2 and type 3, but not type 0 necessarily. And type 2 can implement all type 3, but not necessarily type 1 and type 0. And type 3 can implement only the regular grammar. Okay, so that is all in this video, and in the next video I'll start with the DFA. Thank you so much.